So this problem is very similar to that one that we just did on our own, or sorry, all together just before. We've got a 2 kilogram mass, initially stationary, which means that its initial velocity equals 0, and here it has this force being applied for 2 seconds. So our impulse would be the integral of 3t squared dt from 0 to 2. This integrates really nicely to just t cubed, which gets us 8 Newton seconds. Well, that's our impulse, which is also our change in momentum. So our change in momentum is 8, and that equals our final velocity, which I'm going to be looking for, times our mass, plus our initial velocity, which is 0, times our mass. So that initial velocity just goes away. So what we get, dividing by 2, is that the final velocity equals 4, and we're talking about meters per second. So this was the right answer. Okay, this is a little bit of a harder problem, but so what we're looking at is a car crash. Everyone's going to be okay, so no need to worry. But here's our wall, and here's our very interesting car shape. It's an 80 kilogram car, and it's coming in and it crashes in at 30 degrees, hits the wall, and it's going to bounce off the wall at a 10-degree angle. It came in at 70 meters per second, and it bounced off at 50 meters per second. Just to make this a little bit more clear, it's 10 degrees. Okay, so here's our situation. Clearly there's an impulse being delivered to the car right there when it hits the wall, and that impulse, the result of that impulse is a change of momentum, change of direction, velocities were affected. So let's draw this situation slightly differently. And the way we're going to draw this is thinking about our initial velocity, which is in this direction, our initial momentum rather. So here's pi, and then p final. And because impulse is a vector, what we want to do is break things down into their vector components. So the impulse delivered in the x direction, what we're trying to do, sorry, I should have said this at the beginning, but the purpose of this problem is to find the impulse and the angle of the impulse. So impulse delivered in the x direction is simply the change in momentum in the x direction. So it would be the final momentum in the x direction, which is its mass. And I guess we could just leave the mass way outside. So it would be mass times velocity. So its velocity was 50, because this was a velocity of 50, times cos of negative 10 degrees. Negative because it's below the x-axis. And then minus, it had a velocity of 70 meters per second, so minus 70 cos of 30. And this is roughly negative 910 Newton seconds. And the impulse in the y direction, well, in the y direction again we're going to have the 80 for its mass. The final momentum, well, the final momentum was 50 sine of negative 10 minus the initial momentum, so 70 sine of 30. And this equals roughly negative 3,500 Newton seconds. Okay, so then the total impulse delivered would be the square root of their sums, just like we've done a bunch of times before in different types of vector quantities. So we get roughly a magnitude of, well, whatever that is. I think it's like 36 something Newton seconds. Maybe roughly 3,600. Not quite sure about that value, but you could calculate it. And then here's the interesting part. What angle is the impulse being delivered? Well, we need to be careful here because your instincts probably are right to say that it would be the inverse tan of jy over jx. But when we do that, we get a value of 75.4 degrees. Why is that weird? Well, let's think about that, going back to our original graph. That would be like the impulse being delivered in that direction. Does that make sense? Clearly it doesn't make sense. It doesn't make sense because if the impulse were delivered in this direction, the object would speed up in the x direction and speed up in the y direction, not, as we saw, slow down in both. Here we need to remember an important idea about arctan, which is that when we take arctan, the number we get is plus 180k. In other words, the value could be the 75 degrees that we found, or add 180 to it, or 180 more, which will get you back to the same place. So if we were to add 180 degrees to this, or subtract 180 degrees, however we want to think about that. And let's think about it in terms of subtracting it, because it might be easier for us to see. So if we subtracted 180 degrees, and just remember for trig, k is a integer, 1, 2, 3, or 4. So if we let k be -1, what we're getting is an angle that equals -105 degrees, roughly. And this angle makes a lot more sense in terms of the angle of the impulse delivered. That's being, let's use a different color. That's in this direction, 180 degrees opposite of what we found. And an impulse in this purple direction makes sense because that's going to slow us down in both the x and y directions. Okay, there we go.